this session. Alexander is going to talk about accretion flow, geometry, and timing properties of ULX pulsars. Alexander, you can start.
Okay, do you see the slides?
Yes.
Yes, good. Sorry, I have problems with my camera, but I will show my slides. Okay. I'm going to speculate a bit today about possible timing properties of ULX pulsars caused by the geometry of accretion flow. After the talk given by Matteo, we see that there is a definite problem. We still do not have a coherent theoretical model for ULX pulsars, which we all would be agreed on. And we still do not know what's the magnetic field strength at the neutron star surface there. However, as I see gradually predictions of different groups moving towards kind of normal magnetic field strengths, about 10 to 12, 10 to 13 Gauss, but still we do not agree on the basic features of geometry of the accretion flow, and we don't know what's the relation between the mass flow rate from the donor star and mass accretion rate to the neutron star surface. And one of the biggest problems is that we don't know still the relation between the actual and apparent luminosity of pulsating ULXs. In my talk, I will consider two different and maybe opposite geometries and timing features of both of them. The one geometry is related to the possibility of strong advection in accretion disk. Here we have outflows, but still the most of energy is released at the neutron star surface. In this geometry, the outflow is strongly affected by accretion luminosity onto the neutron star, and geometrical beaming is insignificant, which basically means that the actual and apparent luminosity are close one to another. And another geometry represented on the right is constructed under the assumption that advection in accretion flow around neutron star is insignificant. In this case, we can use directly results from Shakura-Sunyaev paper, and it means that the system loses a lot of matter from supercritical accretion disk, and only a small fraction of initial mass accretion rate reaches the inner disk radius and then neutron star surface. The outflow geometry in this case is not affected by radiation pressure from the central object, and strong geometrical beaming is expected for observers looking to the systems from certain directions, mainly from the directions located close to the axis of symmetry. Let's start the discussion with the second model, with a strong beaming. This model requires strong luminosity amplifications in known ULX pulsars. Here we are talking about amplifications factor of tens and even 100 for the brightest pulsating ULX discovered in galaxy NGC 59907. There is, of course, some positive features in this model. There is no any specific requirements for neutron star in ULX. And in particular, there is no need for a neutron star to have a strong magnetic field. But I see that there is some problem, at least two big problems in this model. The first one is compatibility between large pulse fraction observed in pulsating ULXs and strong amplification of the luminosity. And the second problem is basically observations of bright X-ray transients, where we do not see any specific features of strong beaming at the peak of the outbursts. Recently, it was proposed by Andrew King and his co-authors that detection or non-detection of pulsations in ULXs in this particular geometry is a matter of coincidence. There should be a lucky combination between rotation parameters of a neutron star in order to get pulsations. Today we know 5 pulsating ULXs, and there are 300 ULXs in general, and 15 or like whatever told 20. There are only 20 ULXs with sufficient statistics to detect any pulsations. And in 1/3 of that ULXs, we have already detected pulsations. So we can speculate that high pulse fraction is a typical feature for ULX pulsars. And we can guess that number, that the amount of neutron stars among ULXs is large. So we can test the model with a strong beaming. We can try to get simultaneously large pulse fraction and strong amplification. The model can be simplified and reduced just to a few parameters. One of the parameters is geometrical thickness of accretion flow and outflow. The another is H. The another parameter is the inner disk radius of accretion flow. And there is also parameters which describe rotation of a neutron star in reference frame of the accretion flow. Using this set of parameters and applying Monte Carlo simulations, we're able to trace a history of each photon originated from the neutron star surface. We can account for GR effects, and we can account for reprocessing of X-rays by the walls of accretion cavity. And finally, for each set of parameters, we can reproduce the pulse profiles. Of course, these pulse profiles will be different for different observers located in different directions from the system. Out of the pulse profiles, we immediately get the average flux detected by the observer and the amplification factor, which determines the relation between actual and apparent luminosity. Also, we get the pulse fraction. Typical distribution of X-ray energy flux over the direction is represented on the plot here. The flux is amplified along the axis of accretion disk. It's a quite natural result. Also, it's quite natural that the thickness of accretion flow affects the amplification factor. The thicker the accretion flow, the stronger the amplification. Assuming a certain distribution of neutron stars over parameters describing their rotation, we can get two-dimensional distribution of ULXs over the amplification factor and pulse fraction. In case of small ratio H to R, it's a case of not a very geometrically thick accretion flow. We get this kind of distribution. You see it on the plot. Amplification is there sometimes, but it's not very strong, and pulse fraction can be high. But if we make accretion flow thicker, then the amplification, of course, becomes stronger, but typical pulse fraction drops. And at very geometrically thick accretion flows, we can get strong geometrical beaming, but the pulse fraction goes below 10% typically. Here on top right picture, you can see the distribution of sources over the amplification factor for different ratios H to R. And the dashed lines corresponds to the sources which produce pulsations with pulse fraction above 10%. So what we basically see, we see that it's very hard to have simultaneously strong amplification due to the geometry of the accretion flow and large pulse fraction. And I think it means that detection of strong pulsations from ULXs is inconsistent with models with strong geometrical beaming. Let's take a look now at the case of system with advection and without strong geometrical beaming. In this case, the outflow from radiation pressure dominated part of accretion disk blow away some amount of matter, but the most of matter accretion rate reaches the inner disk radius and then neutron star surface. The mass flow covers the magnetosphere of a neutron star, and the distant observer basically see the envelope instead of a neutron star in the center. The envelope probably affects the observational features of UL axis, like X-ray energy spectra or pulse profiles, which become smoother as we see them in observations. In addition to that, the envelope affects the timing properties of accreting neutron stars. It's known that there is always stronger periodic variability in X-ray flux in accreting strongly magnetized neutron stars, X-ray pulsars. The variability is caused by different things, but one of the main things is mass accretion rate fluctuations originated from the disk. These kind of fluctuations are well studied in black hole binaries and less understood in X-ray pulsars. Nonetheless, we know a few things pretty well. We know that there should be a break at high Fourier frequencies in the power density spectra. This break corresponds to the dynamo frequency at the inner disk radius, which, by the way, should be close to the local Keplerian frequency. And if you can detect the break in observations, and if you have a guess about relation between mass accretion rate, magnetic field strength, and the inner disk radius, you can get the estimation of magnetic field strength just out of timing analysis. And that is already used in analysis of classical X-ray pulsars. The examples of typical power density spectra of X-ray pulsars is given here on the right plot. Two spectra corresponds to two different luminosity states, and we clearly see changes in the break frequency, which correspond to changes of the inner disk radius. That is why we are caring about timing properties of UL axis. Timing analysis might be useful in probes of magnetic field in UL axis. However, we remember that there is an envelope, and the envelope change things a lot. The envelope prevents photons from immediate escape from the system. Because of that, high frequency variability is expected to be suppressed. And again, tracking numerically the history of each photon in the system, assuming some specific geometry, we can get the estimation of suppression factor applied to the power density spectra in UL axis. The suppression factor is a function of Fourier frequency and represented on the right bottom plot. Sorry. Different curves corresponds to different typical optical thickness of the envelope. We expect that optical thickness should be above 10. So the power density spectra is expected to be strongly suppressed above the certain Fourier frequency, and we expect to have a break at the high frequencies. The break frequency is represented, is dependent on the mass accretion rate and magnetic field strength in ULX. Assuming typical mass accretion rates in ULX is about 10 to 20 grams per second, and magnetic field about 10 to 12 Gauss, we can make an estimation of the expected power density and say that suppression should happen above 1 Hertz. Okay, let's summarize. In case of considered geometry, the photons originated from the envelope, and the photons is originated from the envelope, and system produces smooth pulse profiles and geometrical beaming is small. But what is important, if we will get at some point power density spectra, we do expect strong suppression of variability. And now I'm coming to my conclusions. We have considered two different geometries, and in the case of geometry with advection, we don't expect strong beaming, and we expect suppression of periodic variability at high frequencies. And in case of systems with strong geometrical beaming, it looks that it's in general very hard to get pulsations of high pulse traction. So that's my conclusions. If you have any questions, I'll be happy to give comments. Thank you.
Thank you for your talk and keeping the time. Good. So any question or comments? I see one question here, but that's to Matteo. Perhaps Matteo can answer that on the chat window. Sylvia, go ahead and ask your question.
Sure. On this plot, okay, first of all, thanks for the talk, always very, very clear. In your picture on the left, there is the scenario with advection. I do have a problem with that scenario. There are some ULX for which the spectrum is fitted with the double black body or a disk black body plus a black body, one component from the disk and the other is told to come from the thick envelope around the magnetic line, the sort of donut that you have at the center, right?
Yes.
Okay, there is one source which has a luminosity larger than 10 to 40. In that case, I make a few calculations back on the envelope. The thickness of the curtain of the donut is such that the temperature which emerges is very, very cold. It doesn't fit the observed one. Basically, at very high luminosity, the optical depth is too high, and the radiation which is trapped in the cavity is dramatically reprocessed. So it looks to me that, at least in that case, some sort of binning is required because the model cannot self-consistently explain.
Yeah, I have a few comments on that. First, as far as I understand, the temperature of radiation going away from the envelope should depend mostly on its area, right? Also, I think that the temperature on the envelope should depend on the coordinate on the envelope. So there is no.
I did the calculation point by point. We did the calculation point by point. It's very preliminary. So I'm talking about the maximum possible temperature that can emerge, which is not even necessarily in view. We can discuss, but I think there is a problem.
Additional thing. I haven't shown these results, but very recently we have tried to make particle and cell simulations of the accretion flow in between the inner disk radius and neutron star surface. And it looks that it might be hard to have stable accretion flow in between the inner disk radius and neutron star surface. And it might be that these instabilities in the accretion flow might cause appearance of relatively hard photons in spectra, but still we have to test our model. And
yeah, we also are preliminary, but thank you very much.
Okay, so if you have other questions, you can just type on question and answer window.